can move to the next presentation by Giorgio Paolucci. So Giorgio Paolucci did his studies at the University of Rome, La Sapienza, and then he is now at the Synchrotron Elettra in Trieste, in Italy. But in the past, he's also been for 5 years the scientific director at Sesame. So, Giorgio, can you now share your presentation?
Yes, I hope so. It worked before, so should work.
Okay, we see
Okay.
everything. Yeah. Thank you.
Okay, so good afternoon, everybody. It's afternoon here. It's a pleasure to be here again, and I'll give you an introduction to photoelectron spectroscopy, which is a field which was extremely important in synchrotron. I mean, that most experiments in synchrotron started in this field because it requires rather softer radiation than other applications. We have just heard a presentation on the newly built build line in Sesame, which covers that photon energy. And I guess that after my presentation will be a presentation on the photoelectron spectroscopy branch of the same build line. So it's a good arrangement of talks. So I will, during my presentation, I'll give you some basic ideas of what photoelectron spectroscopy is, what are the physical phenomena underlying it, what are the kind of information you can get, and then I'll show you some examples. I will not refer specifically to particular beam lines because that are going to be presented by other people. So a photolation or photoelectron spectroscopy experiment is basically an application of the photoelectric effect. There are two Nobel Prizes related to the photoelectric effect, one to Albert Einstein for the interpretation in terms of photon energy of the photoelectric effect, and the other one to Kai Sigban in the 70s for the development of this method. So basically, you have photons incoming onto a sample, which we imagine in this case being a single crystal, but it can be also other kind of experiments, of other kind of samples. You can apply magnetization if you wish to change to look at the magnetic details of the sample you're investigating. But basically, what you do is that you collect electrons which are kicked out of the sample, and you measure the kinetic energy, which is given by that relation which you see in green in this slide. You can measure the spin as well in some sophisticated case. I will not talk about the spin result photoelectron spectroscopy. You can change the polarization and look at different states. So the basic idea is that you excite electrons from the sample, and because you know the characteristics of the incoming radiation, and you measure the angle of emission and the kinetic energy of the photoemitted electrons, you get information about the sample itself. What you do here, so this is a schematic in which you have on the left side, you see the energy levels of the sample, you see all the potential due to the atoms, which are modified when you move towards the surface of the sample. And basically, you move these electrons, which are occupying states below the Fermi level. You kick them out. They go through a potential barrier due to differences in the work function, and then they enter into something that looks at the kinetic energy. And so first you excite them, then they are transported to the surface. and then they go through the vacuum, and then they go into the analyzer. So the energy you measure is to a first approximation, assuming that the electron states are not changed by the phenomenon itself, which is of course an approximation, it's not completely true. But to a first approximation, one can say that you measure the binding energy by this formula. So you subtract the binding energy from the photon energy, and then there is a constant which is due to the instrument we're using. Okay, so this model which I just described is also known as the three-step model, in which you have the excitation, the transport, and the analysis. Okay, in this process, there are a number of parameters which one has to look at. The number of photoelectrons you get is, I'm using here the same colors. So the violet arrow is the incoming radiation, and the green is the flux of electrons which are going outside of the sample. So this is a very, very simple scheme. So what I'm trying to sketch here is that the radiation is absorbed while traveling to the atom you're looking at, and then the electron wave is also attenuated, or the number of electrons is reduced while traveling through the sample. And the number of electrons you get out of the sample is somehow is proportional to the number of atoms you get in the specific atom you want to look at. It depends on the photon flux. It depends on the probability or the differential cross-section of this particular level you're looking at, which we'll describe in a minute. And then there is also proportional to the probability of no loss escape. So the probability that actually electrons are traveling through the sample actually go out of the sample. And then you get other two components which are basically related to the instrument. So the first three multiplying factors in this very, very simple formula have an influence on the, are influenced by the photon energy you are using. The photon energy you're using can be a synchrotron, and this is a school about synchrotron, but not only. So you can use standard laboratory sources, because just to extract the electrons, if you measure the kinetic energy, you can use fixed energy. So the wavelength we're talking about is from 1000 to about 5 angstrom, which corresponds to a photon energy of 10 to about 1500. Actually, nowadays people tend to go above 1500 electron volts. You can use laboratory sources which are basically using something related to the properties of a material. So, for example, you use helium-1 alpha radiation, which is 21.22 eV, and that's it. Or you can use aluminum K alpha or magnesium K alpha radiation, which are also fixed in energy because they are based on the K alpha emission. You can use lasers, or you can use synchrotron. A synchrotron is, of course, expensive. much more than a gas discharge lamp. However, you can do experiments which you cannot do in the lab. The typical electron energy analyzer is shown here. So it's basically a spherical condenser. And the good thing about the spherical symmetry is that we know exactly, we can calculate trajectories very well because their ellipses exactly like in any central field, like for example, the orbit of planets in the solar system. So, and basically, if you look at this, there is a slit where electrons enters, and you define a pass energy, which is the formula is shown in the bottom left corner of this slide. And if the energy, and on the other side of the entrance of the electron, so in the right-hand side of this slide, you have a detector, which is normally a position-sensitive detector. So electrons whose energy is higher than this mean energy will reach the detector away from the center of the two spheres, while those whose energy is lower than this energy will reach the detector closer to the inner sphere. So basically in one shot you get a kinetic energy spectrum. In the other direction, so the direction perpendicular to the other direction of the detector, by arranging the optics, the electron optics in front of this basic instrument, you can measure the angle of emission of the electrons. But this gets very complicated, but just to tell you that can be done. So this is a position-sensitive detector. So it's basically mounted on a flange, and then you get a 2D, you can measure X and Y position of where the electron enters. And a typical modern like Texas, I hope I pronounce it correctly, so the Turkish binary sesame looks more or less like that. So you have an undulator source, and of course you know everything about undulators from the previous days. You have some sort of monochromator in between. Then you get a focusing optics, which in this case is a toroidal mirror, and this is also the case at Sesame. And then you measure the spectrum of photoemitted electrons. And as shown here, in one direction you get the energy, and the other direction you get the angle. So in one shot you get pictures like the one in the bottom of this slide, which are related to emission coming from different points in the Brillouin zone of the band structure. So, so you see immediately what, okay, this is how tunable is the energy, the typical synchoradiation facility. Now we go and study what the three-step model is. But just before we do that, I just want to stress that by measuring the angle of emission of the electrons, you can get information of the band structure of the sample. I hope many of you know what the band structure of solid is. And you measure basically occupied states. So that's different from, for example, absorption spectroscopy, which was the mentioned before, where you get a combination of initial and final states. So you have to decouple the information from the two states. In this case, since we are extracting the electrons all the way away from the sample, the main information is coming from the initial state, which are the occupied states. And so the first step in the three-step model is the excitation, as I said, so which is shown here. The excitation is not different from the absorption part. I mean, you are basically absorbing the photon. And the photon emission cross-section depends on the energy of the photons, and it depends also on the material. For example, if you look at these levels, so you took the aluminum 2p, the carbon 1s, the oxygen 1s. This is the way they behave. You see that overall the photoemission cross-section decreases as the energy increases, which is one of the reasons why I said that you normally prefer to work at low energy. So you had the onset of photoemission is, of course, the energy of the core level you're looking at. And depending on the energy, you see that the absorption is favored or non-favored. And as I said, all of them decrease with photon energy. And you see they decrease a lot because if you look, for example, the aluminum 2p, you get 2 orders of magnitude if you move from, say, 200 to 1400 electron volts. So it decreases a lot. And I'm going to try to explain to you why this happens. Now, I apologize with those of you who are not physicists, but I am a physicist, so I tend to talk in physics terms. So for those of you who are not physicists, the next few slides will be extremely boring. So the probability of exciting an electron is given by solving this Hamiltonian. So this is the Hamiltonian of an electron external electromagnetic field, which is represented by the vector potential A and the scalar potential phi. And this is the relation between the electric field and the magnetic field, okay? So these are just definitions. So this is the Hamiltonian. So this includes V in this equation is the potential of the sample you're looking at, and depends, of course, on the position. And P is the electron momentum inside the sample. So for a free electron, the terms with A and phi would not exist, and then you get the Hamiltonian of an electron in a field, okay? Now, if you look at that, of course, you have to expand the square, and we assume that the divergence of the vector potential is 0, and we assume that phi is also 0. That can be done because there is some freedom in choosing the potentials. And then if you do this choice, then you observe that the vector potential obeys this differential equation, which is the equation of waves, which is what we want. I mean, we want the description, we want to describe an incoming wave. Okay, so let's keep this in mind. So we expand the square, and you have to keep in mind that you have to distinguish, since you have a dot product between P and A, you have to, they normally do not commute. So you have to write explicitly, although because with transverse gauge, they do commute. So that is the expansion of just the square term, and exactly the equation I wrote before, and we insert it in Schrödinger's equation. So we put it in front of the wave function. And so you do some basic algebra, and you come up with this formula in which we have neglected the square terms. The square term E over 2mc square times A square, because we know that A must be small with respect to the electromagnetic field, the atomic electromagnetic field, so that terms can be neglected, and it is moreover divided by C square, and we know that C is a big number, so we neglect that. That is not a good approximation. And so we come up with this equation, which is exactly what we want, because this equation is in the form of the basic equation of the electron in the sample, plus a perturbation, which is this A dot P term. And so we can use, so this is an Hamiltonian in this form where H1 is the perturbation. And so if we assume that this is just, I mean, this H1 in which we have assumed the nabla terms is just it comes from the basic quantum mechanics definition of the momentum operator. And because the vector potential effect wave equation, we can express it in terms of plane waves. So if we insert this formula for A into Schrödinger's equation, and we know that, I mean, these are the relation between A and E, we get basically this expression for each wavelength. So basically, you see here that we have the Dirac delta for the function, which basically impose energy conservation. So the energy of the final state, the difference between the energy of the final state and the initial state must be equal to the photon energy. This is well known. I mean, you know that this is, if you want, if is a formal way of saying what I said at the beginning. So you are translating the electrons up by h bar omega. And you have this matrix element between F and E and I, which is what we are going to discuss. And because of the form of H1, which is which we write in the second line of the equation, where the exponential of IQR is, I mean, we can we can stop the series expansion just to the first few terms. And because the modulus of the wave vector of the incoming photons is 2 pi over lambda, which means that 100 eV, it is of the order of 0.05 angstrom to the -1. And because we are talking about distances of the order of angstrom, now 1 times 0.05 is, of course, a very small number. So we simply forget anything which is after 1 in this expansion. And okay, this is the formal way of saying that we assume that in spite of the fact that we have an incoming wave on our sample, the actual electromagnetic field is constant in the region of interaction. So we can neglect the fact that it's actually moving, and we say, okay, that's constant. And this is an extremely good approximation unless you go to extremely high energies, when, of course, 2 pi over lambda becomes larger. So these are the basic formula, which you get by neglecting the variation. Okay, so this is the formula, the probability of exciting an electron from initial state I and send it to final state F. Okay. These are two ways of expressing it, and there are other ways of expressing it, which are shown here, because of, so you can write it in terms of the potential or in terms of the distance. So this is the so-called dipole velocity approximation. This is the called dipole acceleration approximation. This is the dipole length approximation. These are all the same. They are different in practical terms because of the approximation you have to include when you calculate the initial and final state. I remind you that in quantum mechanics, there are very few problems that you can solve exactly. So it's basically the potential well, the harmonic oscillator, and the hydrogen atom. So that's it. Anything which is more complex than one of those terms is calculated with some approximation. Okay, so we define this, and you get this, and which is the image I showed you before. As I said, that decreases with photon energy, and the reason is that when you go to higher energy, you are basically throwing or exciting your electron to final states which are larger and larger in space. And so the overlap between the two is very small, so you're actually decreasing the probability that that occurs, okay? Okay, then you can express it in terms of spherical harmonics, and you can find, for example, I will skip some of the slides. This is the distribution of photoelectrons, which is cosine form for an atom in which you excite an S level, so spherical symmetric, and that is not surprising because you get a distribution. I mean, if you excite an S level, the final state is a P level, so the distribution of photo emitted electrons is very similar to a p orbital. In XPS, so a photoelectron spectrum looks like that. This is you can find it at this website, which is a public one. So you can go there. So this is a silver sample, and you can. This is excited with a standard laboratory source. So in this case, it's aluminum K alpha, so it's a bit more than 1.4 keV. Indeed, as you can see, the minimum binding energy is 1.4 keV. And all these peaks are related to, apart from the low energy ones, which are called Auger, and I will not go into the details of Auger spectroscopy, but all the others are related to electronic states in the silver sample. So you see the silver 3D at about 380 eV, and you see the valence level, which are mainly formed by the 4D states, and so on and so forth. This is the zoom, if you wish, of the same spectrum close to the Fermi level, which is the zero of our energy scale. So, and you can see that between 0 and say 3.8 eV, you get this monotonic behavior, which is what you expect from a simple metal, because that reminds you of the Fermi-Dirac distribution. And then you get the 4D levels, which are very localized in energy. The 4D level of silver has a peculiar behavior as a function of photon energy, in the sense that if you look at the cross section, forget about the the red line here, which is another parameter which we will not describe, you see that there is a minimum at, I mean, you get a maximum and then a minimum in the cross section. And this is a phenomenon which is known as Cooper minimum. This Cooper minimum occurs in particular circumstances when the initial state has a node in the wave function. So this is the relative reference. And the fact that some atoms, some levels exhibit this behavior is very useful. For example, if you look at this real measurement from Horn and co-workers, and you can see the behavior of the photoelectron spectroscopy spectra as a function of photon energy. So this is the valence band of an alloy, which is shown. So it's aluminum, palladium, manganese sample. And then you compare the behavior of the 40V peak, which you can see it goes up and down when you change the photon energy. And then if you look at the relative cross section, you see that the minimum occurs at 100 eV. If you look at the right-hand side of the picture, and this is exactly where we see the minimum in the intensity of the 4-electron volt peak. So we can safely say that that peak is mainly associated with palladium for the electron. So by using this trick, you can actually understand how what is the weight of the information of the bonds. Let's skip some of the slides because we're running out of time. When you look at this part of the kinetic energy of the photoelectron spectroscopy, so the region near the Fermi level, you can actually also look at the angular distribution. And the reason is that, as you can see, this is the first figure I showed you. So basically, you can imagine that the emission angle is related to the component of the wave vector of the outgoing electron, and which you can decompose in a component which is parallel to the sample surface, which in this case is a single crystal, and a perpendicular one. Now, if you remember what I said, that the electron has to overcome a potential barrier to go out of the sample, you can easily imagine that the perpendicular component of the wave vector is not conserved in this process. But nothing happens in the direction parallel to the surface. So that component is conserved. And that means that you can actually map the energy. And this is one of the first applications of synchoradiation. This is a very old, this figure is taken from a very old paper, but as you can see, it was published in 1980. So it was even before I got my master's degree, so to tell you how old this paper is. But nevertheless, it shows you that the basic feature here, these are measured normal emission. You change the photon energy in a range which goes from 25 to 100 electron volts, and you see that the position of peaks changes, and you can compare that to the calculated band structure, And you see that the position agree. I mean, you can actually very effectively verify what the calculations have shown. I remember when I was exactly in the master courses, I remember attending a lecture in which these spectra were shown, and the professor told us, now I believe in band structure. Before these results, I thought band structure was just invented by theorists, which is I know that our chairman is a theoretical physicist, so he will appreciate this joke. Anyway, I will skip other, just to show you a nice example of, this is a bidimensional system. So in a bidimensional system, you map directly the band structure. So this is a metal, a silver metal absorbed on a platinum, surface, and you can see the dispersion directly. And of course, being a quasi, being a noble metal, you get quantization in the vertical direction, and you get free electron-like behavior in the other direction. This is another nice example of dispersion. This is a more recent result. It was measured in 2010. This is a dispersion of hydrogen-induced modification of the band structure of graphene. And you see the opening of a gap because what we are measuring very close to the Fermi level. You see that in pure graphene, you get this Dirac cone type of band structure. So you go straight and then it crosses, and then you get the unoccupied part above the Fermi level, which we don't see because, as I said, we only see the occupied part of the electronic structure. But then as you dope your sample with hydrogen, you see that actually the top of the valence band goes down by a few hundred millieV. And that tells you that you're opening a gap in the band structure. If you go to high energy, we can, apart from the, so you don't look at the energy dispersion. The core-level photoelectron spectroscopy, or XPS or ESCA, depends on the element you're exciting. You've seen before the spectrum of silver. You can look at different oxidation states. There was a question before about looking at different oxidation states, and you do that with this spectroscopy. Then maybe we'll say a few words about photoelectron diffraction, although time is running by. So if you take a piece of aluminum and as it is from air, and you put it in your vacuum chamber, you measure something like that. So this is aluminum. And as you can see, aluminum is not the highest peak. You get a huge oxygen 1s peak, and you get a relatively big carbon 1s peak. And this is because of contamination. And the reason is, as you know, aluminum oxides very easily. And because we are looking at electrons whose kinetic energy is of the order of 100 or a few hundreds electron volt, one has to keep in mind that the probability of escaping is extremely I mean, the probability, the mean free path of electrons depends on the kinetic energy, and it is very slow, very little at low kinetic energy. If you can see, is of the order of few to few tenths of angstrom. And because of that, this spectroscopy is very good if you want to look at the surface of your sample. So you're looking just at a few atomic layers of your sample. And okay, if you zoom on that spectrum, this spectrum, I mean, if you look at the zone around the aluminium 2p and 2s, you see that there are various components. One can be associated with the metal, and then one is associated with the oxide, and that is what I was saying before, that you can actually distinguish the oxidation state. Because why is that? Because if you imagine you form an oxide, what happens is that you're transferring electrons from the metal to oxygen, and because of that, the remaining there are fewer electrons on the metal site, and because of that, the energy shifts to higher binding energy. So normally the oxide has a higher binding energy than the metal. There are a few tricks involved in this statement, but normally the peak related to the oxide is higher energy in metals. And then, of course, if it is not oxygen, if it is another atom, you can actually look at the changes. You look at the tables and model samples, and you can get information of what kind of oxidation state they're looking at. And this is easier in this spectroscopy with the limitations we have in this spectroscopy compared to absorption, for example, because this spectroscopy requires vacuum and you're looking at the surface. So if you want to look at the bulk and you think that the surface is different, that's not a good idea. On the other hand, you're basically separating the initial and steady state effect. I mean, you don't have final state effect, so you can think in very simple terms. Now, when you have even a simple metal without any other component, so if you have just one metal, but because it's a single crystal and you get the surface, and we are looking at basically the sample, you can actually see the difference in oxidation state, even if it is just metal, just because you are putting the surface, you are cutting your sample, and this is what you actually measure. This is a spectrum we measured a long time ago. This is a rhodium 100 spectrum. This is the 3D 5/2 peak, was measured low temperature, and you measure, you clearly see two peaks in this case, separated by something of the order less than 1 electron volt. And one is associated, the green one is associated with bulk, and the blue one is associated with the surface species. How do we know that? We know that because if you put some gases on it, the component 306 electron volt disappears. And actually it shifts, as you can see from this, I hope, yes, from this movie here, you see that if you expose that, it's another surface of rhodium, but that doesn't change a thing. You see that while oxygen is absorbed, and we are just looking at what happens at the rhodium site, you see the disappearance of the surface component of the spectrum. And then you see, I'll show it again. Oops, sorry. You see that the yellow component, which is the clean surface, disappears. And while that disappears, you see another component which is rising, the two components. Then that stops, and then you get the bluish component, which is the bulk, which becomes the dominant, and the other one saturates. And that is because you are removing basically clean rhodium atoms, and you bind it to oxygen, and so that changes their photon energy. Now, I have some more examples which I will skip. You can combine the method with other tricks. For example, one thing that you can do with modern synchrotrons, or I mean, by this way, you can basically you can focus your beam to a very, very small area of the surface. So by moving the sample in front of the beam and of the analyzer, you can get a nice maps of your sample. You can, this is for example, an alloy again with chromium, and it's a chromium iron alloy in which you put a component. Then you can see the distribution of the various components on the surface, which is with the resolution. If you look at the first image in the top left of this slide, if you look at the resolution is the order of I mean that bar is 2 microns, so the resolution is of the order 100 nanometers, but you can do even better than that. Photoelectrons, when they go out, they undergo scattering with the neighbor atoms. So this is what happens basically. You excite there are more slides, so when I upload the PDF, you can see more details what is going on. Basically, the photoelectron waves, I mean, since we are talking about waves, they interact with the scattered waves around the atoms, and from that you can get information about the structure of the surface. This is I mean, this is what can be done. So this is an example that was measured a few years ago, that was published in 2023, in which they look at the atomic arrangement of dopants in silicon. And this was done by looking at the angular distribution of photoelectrons. So you can see, you look at what is below the surface, and then by looking at different directions, you get different scattering conditions, and so you can reconstruct what is going on the surface. Several years ago, we were able actually to look at I mean, this was done, as I said, with this standard laboratory source. We looked at the components. This is palladium. As I said, it was published almost 40 years ago. And here what we did was to look at the, when you absorb carbon monoxide on palladium, you get a core level shift, which again is due to different oxidation. So the surface peak, again, identified by the fact that if you do not put SCO, you only get the component on the right. So the one on the left is due to the presence of carbon monoxide. And by looking at the angular distribution of the intensities, we were able to determine the structure. So to summarize, so what we looked at the photoelectric effect. We talked about the sources. Then we went through the quantum mechanical approach of the photoelectric effect. We looked at the photoemission cross-section. We introduced the concept of Cooper minimum. Then we looked at the momentum conservation and how that transfers in the possibility of measuring band structure. And then we looked at the possible application in core level photoemission, going through these element specificity, to its sensitivity to the chemical environment, so the oxidation state. We looked at the photoelectron fraction. We saw that we can look at the time evolution, and we can look at the images with microscopic resolution. So you can do all of what is above at the microscopic level. And with this, I'm over. Thank you for your attention.
Thank you, Giorgio. Thank you for the seminar, and thank you for the joke. And I think it's time now for questions. So Sonia Utterman is the first to have a question. Please unmute yourself. Sonia, are you there?
I can read it.
Okay, yes.
I can read
yes,
it.
so I can yes, I can read it. So up to what degree of complexity can you solve the Hamiltonian and actually calculate the cross sections? You showed the elementary silver. What about molecules?
The cross section is calculated the atomic level. So these for atoms, these are all calculated. If you look at the Elettra website, you can see a collection of the calculations done by Ye and Lindau. Now, since we look at core levels that do not change I mean, if when you form a molecule, core levels are little affected. I mean, you get this shift, which I mentioned, but the behavior as a function of energy do not change. A complete different story is, of course, for the valence levels. For valence levels, of course, they change completely, and that has to be done case by case, but it can be done. Not me. I mean, I normally I was trained to use screwdrivers, not pens and computers, but it can be calculated.
Thank you. So, are there other questions?
May I ask a question?
Sure, Mustafa. Yes, please.
What about the hard XPS and soft XPS? What are the difference between them, and how we can use this difference in our research?
I mean, there are a couple of parameters that you have to keep in mind. One is, of course, this. I mean, when you go to, this calculation stops at 1400 eV. If you continue, they continue decreasing. So the signal is going to be very, very low. But if you take, where is it? This into account, as you can see, this curve rises when you increase the energy. It goes up, up, up. Which means that if you go to very high energy, you can actually get photoelectron spectroscopy from atoms which are well inside your sample. So you stop having just surface sensitivity, but you look at atoms in the bulk. There are experimental caveats in doing that because in order to do spectroscopy, you want to have a very good energy resolution. And as you know very well, it is easy to get, or relatively easy to get 10,000 resolution at 400 electron, 10,000 relative resolution at 400 electron volts, which gives you a resolution of the order of few milliV. But if you go to very high energy, then resolution is an issue. So you do see the levels, but it gets more and more complicated. There have been attempts in the past of doing that, especially at the SRF. We have a project here at Elettra to build a high energy photoelectron for the emission spectroscopy apparatus, so that goes to 4 or 5 kV. So it can be done. You look at the bulk, it is much more difficult.
Thank you.
Thank you. Thank
There
you.
is another question.
There is the next question is by Zahid Mushtaq. So please, Zahid. Okay.
Hello, thank you for giving me the chance to ask some questions. My first question is, what's the advantage of using variable photon energy in synchrotron PS to study braid interferences? And if you want to study surface oxidation of metal, which core level would you choose and why?
Okay. If you want to study barrier interfaces, there are a number of things that you can do. It depends on the specific sample you want to look at. One, if you want, is now I have to if I can find it. Okay. This is a buried atom, so it's the same in buried phase. So you can actually look at the organization of atoms in the two layers. So that is something you can do. In this case, we are showing we are using different angles, but you can play with the photon energy as well, because of course you change the wavelength of the outgoing photoelectron, so you can actually look at different interfering conditions, and so you get more accurate information. The other thing that you can do is that you can apply all what we said to any kind of sample. So for example, if you look at one of the first thing I showed you, this is a simple this is a simple semiconductor that was done using variable photon energy, but of course you can look at any a system of any complexity. So if you have so you can actually choose you can look at the evolution of band structure. Then you can identify, in any case, as I showed you in this alloy, if you are lucky enough that one of the atoms have present the Cooper minimum, if I can find it, you remember that I showed you, here it is. So this is an alloy. And here, as I said, you can determine the origin of the peak, and you can do it. This was an homogeneous alloy, but if you have a layer compound of a buried interface, you can do the same trick. So there are a number of advantages in changing the photon energy. It's not just because we like synchrotrons.
Thank you, sir. Thank you very much.
Thank you. So one last question by Hatem Baba. Hatem, can you please unmute yourself?
I can't read it.
Yeah,
Can we use frequency modulator, double, triple to change soft X-ray to hard X-rays? Okay, that is a very interesting question, like we use with the titanium sapphire lasers. Yes, but you need a laser. I don't remember if you had lectures about free electron lasers. With free electron lasers, I mean, you can do some of the tricks you do with the standard lasers. But I mean, using frequency in order to have frequency multiplications, you need to have a very, very high electromagnetic fields, because the generation of high harmonics depend on the fact that you go into a non-linear regime of the absorption process. So you need very high, and this is still very difficult to obtain with electron-based photon sources.
So thank you. I see Hatem is satisfied. So thank you very much, Giorgio, and
thank you for your attention.
so we now have, let's say,